Sonia, Assistant Professor, Department of Chemistry, St.Josephs College of Arts and Science for Women, Hosur. In this video, we are going to discuss about valence bond theory or Pauling theory. The valence bond theory is nothing but Pauling applied valence bond theory for explaining the structure and coordination compounds. It also the hybridized orbital to form the integral part of this theory. So Pauling was able to amount and even predict the geometrical forms of many complexes and hybrid bonds are involved in their structures. They explain the magnetic properties of many complexes applying this theory. So valence bond theory predicts the atomic orbital undergo hybridization and form the new orbital. In the new hybrid orbital, fill the Ligand orbital overlap with the vacant orbital of the metal and form a chemical bond. This is the valence bond theory. The postulates of valence bond theory. The central metal cation or atom makes the available number of vacant s and s, p or d orbital. So it equals to its coordination number to form the coordinated covalent bonds with ligands. So the vacant atomic orbital of metal are hybridized to form a new sets of bonding orbital that is called the hybrid orbitals. So these orbitals have the same geometry, same energy and definite directional properties. The bonding in metal complexes when a filled Ligand orbital containing a lone pair of electrons overlap with the vacant hybrid orbital on the metal cation or atom to form a coordinated covalent bond. So vacant metal hybrid orbital and Ligand orbital containing the lone pair electron to form a coordinated covalent bond. So the central metal cations is a vacant, so to form a hybrid new orbitals. So then Ligand containing a pair of electrons. So these two combine to give the coordinate covalent bond. So each ligand has at least one orbital containing lone pair of electrons. The Pauling classified into two categories. First one is strong ligand and weak ligand. So strong ligands like cyanide, carbonyl, weak ligand like fluorine, chlorine. The strong ligand have a tendency to pair up the d electron of a metal cation or atom to provide the necessary orbital for hybridizations. So weak ligands do not have the tendency to pair up the d electrons. The d orbital used in hybridization may be either inner n-1 d orbital or outer n orbital. So the complex formed by inner n-1 d orbital is called inner orbital complex, whereas the complex formed by outer d orbital is called the outer orbital complex. So another next one is unpaired electron present in the complex. It is called paramagnetic. If the all electrons is paired, it calls the diamagnetic in nature. So the covalent bonds are formed when two vacant orbitals belonging to two different atoms overlap each other. The electron density in the area between two bonding atoms increases. Result of this overlapping increasing the stability also. So the presence of many unpaired electrons in the valence shell of an atom enables to form a multiple bonds with the other atoms. The paired electron present in the valence shell should not participate in the formation of the chemical bonds as per the VBT theory. The covalent chemical bonds are directional, also parallel or the region bond corresponding to the atomic orbital that are overlapping. The sigma and pi bonds differ in pattern. The atomic orbital overlap with pi bonds are formed from sidewise overlapping, where overlapping along the axis containing the nuclei of the two atoms lead to the formation of sigma bonds. So atomic orbital of the pi bonds to form a sigma bonds. So application of VBD theory, the maximum overlap condition which is described by the valence bond theory can explain the formation of covalent bond in several molecules. This is one of its most important application. For example, difference in length and strength of the chemical bonds in H2 and F2 molecules can be explained by difference in the overlapping orbital in these molecules. The covalent bond in a HF molecule is formed from the overlap of the 1s orbital of the hydrogen atom and a 2p orbital belonging to the fluorine atom, which is explained by the VB. So hybridization and geometry of the complexes. In the coordination number 2, geometry is linear and hybridization is p hybridization. In the coordination number is 4, there will be tetrahedron or square planar. The hybridization is sp3. In square planar, dsp3. In coordination number 6, there is geometry is octahedral and hybridization is d2sp3 or sp3 d2. These are the example for the coordination number 2, 4 and 6. For example, in ground state, the chromium has 5 off-field orbital in D shell and 1 in S shell. In excited state, the strong field affect the electron donated by the ligand CO. So they are the electrons in the chromium d orbitals, they are paired up and they enters into the electrons donated by the ligand, it substituted into the empty vacant orbital. So this is the D2sp3 hybridization and it is the octahedral geometry. So first one is examples for octahedral complexes, inner orbital complexes. In this complex, oxidation state of cobalt is +3. The valence shell of electronic configuration is 3d6. The cyanide ligands are stronger, therefore causing the pairing of 3d electron. All of the 6 3d electrons are therefore paired and occupy the 3 5 3 orbital. So vacant 3 orbital combine with the vacant 4s 4b orbital to form the 6 d2sp3 IB orbital. So these 6 IB orbital overlap with the 6 filled orbitals of ligand to form the 6 coordinate compound covalent bonds. So the hybridization is d2sp3 and geometry is octahedral. This is the outer orbital complexes. So the oxidation state of ion is +3. The valence shell of electronic configuration is 3d5. The F ligands are weakened. There is no pairing of 3d electrons. So all 5 3d electrons are therefore occupied on 5 3d orbital. The vacant 4s orbital combine with the vacant 4b orbital and 2 vacant 5d orbital mix with each other to form a 6 sp3 d2 hybrid orbital. The 6 orbital overlap with the 6 orbital of ligands to form the 6 coordinate covalent bond. So hybridization is sp3d2 and octahedral geometry. And it is for example for the tetrahedral complex. So in oxidation of state of nickel is 2 and electronic configuration is 3d8. So fluorine is the weak ligand, so no pairing of electron will occur in 3d orbital. So none of 5 3d orbital is vacant. So vacant in 4s 4b orbital to combine to give the 4 sp3 hybrid orbital. The 4 hybrid orbital to form a bond with 4 ligands by sharing the 4 pairs of ligand. So it is a sp3 hybridization and it is a geometry is the tetrahedral. So next one is the limitation of VBD. It could not explain the nature of the ligands. It could not explain why the pairing of electrons occur in the presence of strong ligand. It could not explain the color and electronic spectrum of complexes. It could not explain the reaction rates and the mechanism of the reaction complexes. This theory does not provide any quantitative interpretation data about the thermodynamic and kinetic stability of coordination complexes. So drawback is why in some complex electron must be rearranged against and should not explain. Existence of inner orbital and outer orbital not explains. In some complexes, the transfer of electron from lower energy to higher energy level taken place even in the absence of energy supply example. So these are the drawbacks of VBT. Thank you so much.